Today, we're going to combine our ambient, diffuse, and specular lighting together to create a simple lighting shader. Let's go! So let's pick up where we left off last week. So last week I showed you how to calculate specular lighting that you can see here. We went over Phong and blend specular. And then before that, I showed how to calculate diffuse and ambient. Today, we're going to combine them all together to create a cohesive shader that you could use in your projects. The methods for ambient and diffuse and specular that I've shown you so far have been the most simple and basic versions. So the lighting model that we're creating today, I'm just calling simple lighting, because it combines all of the most basic techniques together, and it's very cheap to calculate. So if your engine's built-in lighting is too costly, you could use this instead to improve the performance of your project. In future videos, I'll show you alternate methods of computing the lighting components that are more realistic and more expensive, obviously. Okay. The first thing that we're going to do today is start using a normal map. And so in order to do that, we need to pass a normal map into our normal world input parameter that we have here. And the other thing that we need to do is, last week when I was showing you how to compute specular, we just used the normal vector for those computations, and we actually need to use the normal vector that we're passing in. So a couple weeks ago, I showed you how to set up this, where by default, the input normal is just the world normal vector, but then we can also use another normal that we decide to input. So let's go ahead and connect this up so that our specular is also using our input normal. So we're using our input normal to compute our specular and our ambient and our diffuse. You know what? Before we go any further, I want to take our diffuse here and swap places with our ambient, because in my mind, things go in this order: specular, diffuse, and then ambient. So that may not make much sense to you, but that's the way that I like to kind of organize it. So we have our ambient down here at the bottom, our diffuse in the middle, and then our specular. We're not going to be using our Phong specular for now, so I'll just kind of move it up there out of the way. All right, so we have our blend specular, our Lambert diffuse, and our simple ambient. And we have them, we're passing in our normal vector here. So let's go ahead and save this. We're working in a subgraph right now. And in this version of the shader, you can see our subgraph right here. So let's go ahead and take our normal texture. This is our cobblestones normal, and I've set this texture map to be of type normal and space tangent. And we can just take this and, oh, here's something really important. Notice that in our subgraph here, I named our parameter normal WS, and that WS stands for world space. And it's important that the normal be in world space, because all of the rest of our vectors are also in world space. Our view direction is in world space. Our main light direction is in world space. We're calculating everything in world space, so the normal also needs to be in world space. So what we can do is the vector coming out of our texture sampler here is in tangent space. So what I'm going to do is add a transform node, and I'm going to set it to transform from tangent space to world space. And I'm going to set the type to normal, because this is a normal. Then we're going to pass our normal into our transform node. And it's transforming the tangent space normal vector coming from our normal map, our texture, into a world space normal. And now I can connect this world space normal to my simple lighting node here. And let's take a look at what happens when I save this. Okay, so we've made a massive change here, and we have what looks like a significantly more detailed model because we've passed that normal in. Instead of it looking like a perfectly smooth sphere, now it's got all the lumpy bumps that are coming from our normal map here that we've created. Wow, that's pretty cool. Of course, the specular is not super realistic. Let's go ahead and just kind of bypass that for now and take a look at what it looks like without the specular. Yeah, that's kind of nice. So the next thing that we need to do is, well, we need to fix the specular. But actually, before that, what I want to do is handle this, this base color texture a little bit more elegantly. Because right now, the way that our simple lighting subgraph is set up, we have to do the base color calculations outside of the subgraph. And we actually just want to pass base color into it and allow it to handle that for us. So let's do base color next. So we've set up our normal, and now we need to make a new input for our base color. So we're going to set this to be a vector 3, and I'll just call it base color. And we'll move that up there and save it. And now when we switch back, you can see I have a base color input. So let's go ahead and connect up our base color from our texture here. And now we need to switch back to our subgraph and actually use this base color. So I'm going to drag my base color into my shader. And right here in the shader, I'm adding the Lambert diffuse together with the ambient. And then to combine that with the base color, I just need to multiply the base color result with the diffuse and the ambient added together. Just to make things a little bit more polished, I'm going to set the default value for the base color to 0.5, 0.5, and 0.5. Okay, and then the other thing that I want to do is I want to set our output. Right now we're outputting diffuse and specular separately. But what I want to do with this output is the result of our subgraph is just going to be the lighting. So I'm going to set our output value to just be called lit. And then I'm going to get rid of this extra specular output that we created previously. So we're going to pass our base color input multiplied by our diffuse and our ambient, and then pass that out as lit. And now let's switch back to our shader. And let's just get rid of all this extra stuff here that we don't need. And what you can see here now is we have our subgraph. We're passing in our base color. We're passing in our normal. And then as a result, we're getting lit out, and we can connect that to the base color there. So let's go ahead and save this. And now you can see we've got our nice base color and our normal, and we're calculating the ambient and the diffuse, and everything's looking great. So the next thing that we need to do is add in our ambient occlusion. So we have our mask texture here. And the mask texture has an ambient occlusion in the green channel. So we need to add a new input parameter on our specular lighting subgraph so that we can pass in ambient occlusion. Let's go ahead and do that. So we'll create a new float input parameter. And we'll call it ambient occlusion. And we'll save it, and we're going to set the default to be 1, which is no ambient occlusion. And then for ambient occlusion, we'll just bring this in here, and we'll multiply our ambient occlusion by our ambient value, because ambient occlusion is basically just the object shadowing itself and hiding the ambient lighting. So we can bring in our ambient occlusion value here and multiply it by our ambient, and then pass that out. And now if we switch back to our shader, we can just connect up our ambient, which is stored in the green channel here of our texture. Let's go ahead and do a preview of that so you can see what that looks like. So you can see down here in the cracks between our cobblestones, our ambient occlusion is making things darker because the cobblestones are actually shadowing the object itself. So let's go ahead and pass our ambient occlusion into our simple lighting there. And if we come around the back here where we're seeing mostly ambient, what the ambient occlusion does is it hides the ambient lighting that's in these cracks. We might want to boost up our ambient lighting a little bit because it's coming across as really dark. So let's go ahead and switch over to our rendering lighting tab here. We'll come over to environment. Maybe let's just brighten up our environment just a little bit so that we can see our ambient lighting just a little bit more. Okay, that looks good. And if we disconnect our ambient lighting, let's take a look at the difference. So this is going to be pretty subtle, so you have to kind of watch over here really carefully. If we save this without the ambient lighting, now it's a little bit brighter. But if we connect up the ambient occlusion there, it just gets like a little bit darker. It's kind of subtle, but it makes the ambient lighting a bit more realistic. All right, so we set up our normal, we set up our base color, and we set up our ambient occlusion. Let's set up our smoothness. So we'll come back over here to our subgraph, and we're gonna add a new input parameter, and this is a float, and we'll call it smoothness. And I think for our default value, we'll just set it to 0.5. And then we're gonna do this in the order that it shows up in the master stack. So first we have base color, then we have normal, then we have smoothness, then we have ambient occlusion. All right, so what are we going to do with this smoothness parameter? Let's go ahead and save it, and we'll switch back to our shader, and we'll connect up our smoothness. The smoothness comes from the alpha channel of our mask texture here. Let's go ahead and do a preview of that so you can see what it looks like. Yeah, there's our smoothness data. So it looks like it's smooth on the tops of the cobblestones and then kind of rough on the bottoms. So we can connect that up and pass it in to our simple lighting subgraph and save our result. But what are we going to do with it in here? Our smoothness coming from our texture is a value between 0 and 1. And what we want to use that value to do is to control the size of our specular highlight. When our object is really rough, when it has a rough surface, the specular highlight's going to be really broad. So let's take a look at what this looks like. So if I have a really shiny, smooth object, we're going to have a really high power value for our specular highlight. So if I set this to something like 512, for example, you can see now I have a really small specular highlight, and it makes the object look really smooth and shiny. And when my specular highlight is large, if we set this to something like 16, for example, now my surface is more rough. But the problem with this power value is that it's like exponential. So let me just add a slider so I can show you what I mean. So we're going to go from a minimum of, let's go from a minimum of 8 to a maximum of 512. What happens here is the jump between, like, so my specular highlight is as big as it can be right here. And then as I slide it, you can see that it gets small really quickly. And then once I get to about halfway, the adjustment that's happening is happening really slow. So instead of this being linear, what I'm getting is like this exponential curve where it slows down a lot here at the end. And that's not what I want to be able to put in the specular data in my smoothness texture. I want that data to be linear. And so what I need to do is convert, so this smoothness coming in here is a value that is linear. So a value of 0 in my smoothness means I'm going to get a really big specular highlight. And a value of 1 in my smoothness means I'm going to get a really small specular highlight. It's going to be nice and tight. But I don't want it to be exponential. I want to store the value of linear, but then I want to convert it to exponential once I pass it into my power value here. So the way that I'm going to handle that is I'm going to make a new subgraph. So let's switch over to our project window here. And I'm just going to right click in here and pick Create Shader Graph Subgraph. And for this, I'm going to type, I'm going to name it Adjust Smoothness. And what this subgraph is going to do is it's going to convert the linear smoothness value that's coming from my texture into that exponential value that I need to pass into the power node. So we'll create an input here and just call it in. And then for our output here, this also just needs to be a float value. I'll just call it out. Just nice and simple. And so what we're going to do is this value coming in is between 0 and 1. And this value going out needs to be between like 0 and something really, really high, like 1024 or something like that. So what I'm going to do with my value coming in, the first thing I'm going to do is I'm going to multiply it by 10. And then I'm going to add 1 to it. And then the way that we're going to handle that exponential curve, so the values are linear, but in order to make them exponential, I can just add an exponential node here and make sure that it's set to base 2. And this is going to convert my linear value into a curved value. And I can just pass it out just like that. So we've got our 0 to 1 value coming in, multiply by 10, add 1, and then pass it into this exponential node, which is going to take care of that curve for me. Okay, so if we switch back here to our simple lighting subgraph and drag in our adjust smoothness subgraph, now I can pass my smoothness into my adjust smoothness and then pass that into power. So I've got my adjust smoothness there. I've got my smoothness coming in, and then I've got my specular highlight. So let's save that. And just so that you can see what this adjust smoothness subgraph is doing, let's go ahead and connect up our slider here. And our slider is going to represent the texture data coming in. So we're going to give it a value, or we're going to give it a slider range of 0 to 1, because it's kind of simulating what our smoothness is doing. So when our smoothness is 1, we have a really, really tight specular highlight there. And then as we drag it down, our specular highlight gets larger and larger and larger and just spreads out across the whole shape. But you can see how now that I've added this adjust smoothness in here, we've got a linear action instead of an exponential curve. And it's working much nicer. So now we can represent our smoothness data in our texture between 0 and 1 in a linear space. That's going to work great. Okay, so let's save this, and we'll switch back to our shader here. Oh, you know what we didn't do? We didn't actually hook up our specular highlight. So let's go ahead and do that. So what we need to do with our specular here is we need to multiply it by our diffuse value here. And what that's going to do is it's going to clamp our specular so that it's only happening on the front, so we don't get rogue specular highlights showing up on the back of our object. And then we can just take that and add it to what we have already. So we can add in our specular highlight, and then we can pass it out just like that. Okay, so we have our ambient, we have our diffuse, and we have our specular highlight there. And if we come look over here, you can see that our smoothness texture is working. The tops of the stones are nice and smooth, but then the grout in between the stones are kind of rough. Okay, so what are we going to do at this point? Our specular values still feel kind of bright. And so we have two options. We could do the simple and cheap option, or we can do the fancier, kind of more complex and more realistic option. And that's kind of what you're going to find is the choice that you face all the time when calculating custom lighting. There's always a cheap way to do it and a more realistic, like fancy way to do it. So the cheap way to do it in this case is just to take our specular value there and multiply it by a brightness value. So I'll just add a multiply here. And most objects, when you look at them straight on, have specular values, or they reflect about 4% of the light. So if we just multiply this by 0.04, you can see that we've dimmed down our specular a lot. So there's our nice and bright specular highlight. And there's our 4% specular highlight. And we could just use it just like that. And now that problem is gone, and we're not reflecting as much light anymore. And we could even create a parameter here that controls how bright we want our specular highlight to be. But let's do this in a little bit fancier way. What we're going to do is simulate how reflectance works in the real world. Like I said, objects that are reflecting the light, when you're looking straight at them, they only reflect about 4% of the light. But if you're looking at the object at a glancing angle, they actually reflect 100% of the light. So if you look at a surface at a very shallow angle, where your eye line is almost parallel with the surface, you're going to see a much more reflective object than if you're staring at the object when the surface is kind of perpendicular to your view. Hope that makes sense. And we can simulate that using Fresnel. So what I'm going to do here is add a node that's called Fresnel effect. And if we take a look at this, you can see that this is simulating what that phenomenon that I'm describing. So here in the middle, when I'm looking straight at the surface, we have a value of 0. But then as I'm looking at the glancing angle of the surface here on the edge, we get a value of 1. And just to make this a little bit more realistic, I'm going to raise this to a power of 3 instead. So now we have a surface where when I'm staring straight at it, the surface is dull or dark. I'm getting a low reflectance value. And when I'm staring at the glancing angle of the surface, I'm getting a much higher value. So in order to make this work, we need to plug in our normal to the normal input there. And then we need to use this Fresnel effect. I'm just going to go ahead and delete this multiply so we have a little bit more space. Now we need to use this Fresnel effect as a mask so that we're going to lerp between what is our reflectance value when we're staring straight at the surface? Well, it's 0.04. And what is our reflectance value when we're staring at a glancing angle? It's 1. And so we're going to use our Fresnel to blend between 0.04 and 1. And this is going to become the value that we use to multiply our specular highlight. So when we're staring straight at our specular highlight, it's going to be a little bit dimmer, but then as the specular highlight comes around to a glancing angle, it's going to be a little bit brighter. So let's go ahead and minimize these nodes. I'm going to group them, and we're going to call this our reflectance. And we'll just kind of tuck reflectance here in between our specular and our diffuse. In fact, let's kind of rearrange things so there's a little bit more space. And we'll multiply our specular highlight by our reflectance so that the highlight is dim, when we're looking straight at it, but then at a glancing angle, it's going to be bright. We'll go ahead and save that. And now you can see we have a much more realistic looking response from our specular. So here, if I kind of come around here to the edge where we're looking at a glancing angle, you can see the specular highlights a little bit brighter there. But then when we're looking straight at the surface, it's nice and dim. Okay, so let's do a quick overview. We've calculated our specular and we've calculated our reflectance. We've calculated our diffuse and our ambient, and we've combined them all together and passed them out. And now we have a subgraph that calculates all of the lighting for us. And all we have to do is pass in our base color, our normal, our smoothness, and our ambient occlusion. And we end up with some realistic lighting. Okay, now you might be telling me, but there are some things missing here. We didn't actually do anything with the color of the light source. What about surfaces that are metal? What about the object receiving cast shadows? You know, there are a bunch of pieces missing. So those are the things that we're going to talk about in future videos. I think next week, what we're going to do is add a new input pin here to our simple lighting, and we're going to allow our object to be metal. So we're going to start getting into reflections and that sort of thing. That's going to be really cool. So be sure to come back next week to see how we can turn this into a lighting model that allows us to create metal surfaces. All right, that's it for today. Let's switch over to Unreal, and I'll show you how to do the same thing in that engine as well. Here we are in Unreal, and what we're going to do today is take all of the pieces that we've put together in the last couple of weeks and build a simple lighting model. So we're going to pick up where we left off last week. Last week I showed you how to create Phong specular and also blend specular. And the week before that we learned how to create Lambert, diffuse, and also ambient. So let's go ahead and take these pieces and put them together into a cohesive lighting model. So the first thing that I'm going to do is open up my content drawer here, and we're going to create a new material function. So far we've been creating everything in one material, but what I want to do is create this material function, and I'm just going to call it simple lighting. And inside this function, we're going to do all of the work that we need to do to create the lighting for our shader. So let's go ahead and open up our material function here. And we're just going to copy and paste a bunch of the parts that we've put together into our simple lighting material function. So here's our ambient lighting. I'm going to copy and paste that into our simple lighting material function. So there's our ambient. And we also need our diffuse. So I'll go ahead and copy our diffuse and paste that in. Let's put our ambient down here at the bottom. Our diffuse here in the middle. And then for our specular, we're going to use blend specular highlight. So I'll just select this bit here. And we're going to paste that in here at the top. Okay, now each of these individual components of our lighting need a normal. So let's go ahead and add a function input. And we'll set this to be a vector 3. And we're going to call this normal world space. And we need to add a default for it. So let's just add a vertex normal in world space. And that will be our default value. And we need to make sure that we check this really important box down here so that it's going to use our default. Okay, so there's our normal coming in world space. We need to plug our normal here into our specular, and we need to plug it into our diffuse, and we need to plug it into our ambient right down here at the bottom. All right, and let's just clean this up a little bit. I'm going to move these nodes over here and just make our ambient block not quite so big and bulky. Okay, so we've got our normal coming in, and we've plugged it into our diffuse, our ambient, and our specular. Let's just set our output to be called lit. Let's just wire some of these things up really quickly so we can get an idea of what this is going to look like when we're done. We need to add our diffuse and our ambient together. And then we need to add our specular on top of that. And we're going to revise this quite a bit, but I just want to create like an initial version here so that we can make sure that our results are correct. So here you can see our ambient lighting around here, around the back of the sphere. And then in the front, you can just barely make out a specular highlight right there. And it's fairly small because we're raising it to a power of 256. So we're going to come back and add more features in here, but I just wanted to get the bare bones of this lighting material function set up so that we can add it to our shader or add it to our material and make sure everything's working correctly. So let's go ahead and save that. We'll switch back to the shader that we have been working on. You know, we've got all of our components in here. Let's go ahead and add in our simple lighting material function that we just created. And you can see that so far, all we have is a normal input and a lit output. So for our normal, I'm going to grab our normal cobblestones texture. And you can see that I named the normal input normal WS. So we need the normal to be in world space. And coming out of the texture here, our cobblestones texture is in tangent space. So in order to fix that, I'm going to go ahead and add a transform node. And we can set our transform to go from tangent space to world space. So it's going to convert our tangent space normal vector into world space, which means that now we can plug that into our simple lighting and then plug the output of our simple lighting into emissive color. Let's see what we get. Okay, that's working great. So we've got our normals, and our normals are correctly affecting our ambient and our diffuse lighting and our specular lighting. So everything's working as we've designed it so far. Okay, the next thing that I want to do is add a new input in our specular lighting, or in our simple lighting material function, so that we can bring in our base color. You can see we've got our base color texture here. We're ready to start using that, but we need to add an input in our material function. So switch back to our material function, and let's go ahead and add a new function input. This one's also going to be a vector 3, and we're going to call it base color. And just as a default value, we're going to set it to 0.5, 0.5, 0.5, so it's kind of a gray value. And we'll check this use preview value as default. Okay, so now we can take our input, our base color here, and just multiply it by the combination of our diffuse light and our ambient light. So we'll just add a multiply here and multiply our diffuse and ambient light by our base color, and then connect that up to our specular and save it. Switch back to our simple lighting. Now you can see we have a base color input. So I can connect up my base color texture to that. And now we have something that looks a little bit more realistic. So we have our base color coming in. We have our normal map coming in. And everything's progressing nicely. Okay, the next thing that we're going to do is add in ambient occlusion. So we have a mask texture down here. And you can see that I've named this mask texture ORMH, and that stands for occlusion, roughness, metalness, and height. So our ambient occlusion is going to be in the red channel. So we want to be able to wire our red channel of our mask texture into our lighting function here. So let's go ahead and add a new input. And we'll just come down here for our ambient. And we'll add a function input. And this one we're going to call ambient occlusion. And instead of vector 3, we're going to set it to be a scalar. And we're going to set its default value as 1 and check this box down here. And then for our ambient occlusion, all we need to do is multiply our ambient occlusion by this input. So I'll add a multiply and we'll connect up our ambient occlusion here and then connect it to the rest of the shader. So let's hit save and then switch back to our shader. And now you can see we've got our base color, our ambient occlusion, and our normal. And so now I can connect up the, I think it was the red channel, right? Let's double check again. Occlusion, yeah. So we need to get our ambient occlusion from our red channel and pass it into our simple lighting. And now if we come around the back here, you can see that we've got our ambient occlusion applied there, and it's making our ambient lighting just that much more realistic looking. Okay, so we've got base color, we've got ambient occlusion, and we've got normal. And we're getting to the point where we need to start creating a proper order for our inputs here. And so what I'm going to do is just add some priority numbers to our function input so that we get these in the right order, because I want it to go base color, normal, and then ambient occlusion after that. So we're going to select our base color and make sure that our sort priority is 0. And then for our normal, we'll set our sort priority to 1. And for our ambient occlusion, we will set our sort priority to 3, actually. The next value that we're going to create is our smoothness, and that's going to be a sort priority of 2. So let's go ahead and create our smoothness input. So there's our function input. It's going to be a scalar. And actually, you know what? I know that Unity likes to use smoothness, but Unreal likes to use roughness. So let's use roughness instead of smoothness here. And we're just going to default this to 0.5 and check this box down here. And now we've got our roughness input. And we want to set the sort priority to 2. All right, so let's save it, switch back to our shader. Now you can see we've got base color, normal, roughness, and ambient occlusion. And we can go ahead and connect up our roughness. If we look here, we can see that our roughness, that's what the R stands for, is in the green channel. So I'll go ahead and connect up our roughness there. So we've got our base color, we've got our normal, and we've got our masks texture, and we're using the ambient occlusion and the roughness. We're passing that into our simple lighting function, and now I need to show you how to actually use this roughness value. So we'll come over here, and we know that our roughness value goes from 0 to 1, and our blend specular needs to have a power value that's somewhere between 1 and 1024. And the problem with this power value is that it's exponential, so that, if I change it from 1 to 5, that's going to have a drastic input on the size of, it's going to have a drastic change on what that specular looks like. Let's just go ahead and wire this up so we isolate the specular, and you can see what I'm talking about. If I set this to, let's set it to 2, we're going to have a gigantic specular. And if we change this from 2 to 5, you can see that there's a pretty big impact on the size of that specular. Let's set it to 10. So as the numbers are really low and I'm changing it, it's having a really big size impact. But if we set it to 256, now it's really tight. And then if we change it to like 276, you can see it's still pretty much the same. So our response here is an exponential response. It's a curve instead of linear data. And what we have here with our roughness is linear. It goes from 0 to 1, where 0 is smooth and 1 is rough. Well, let's go ahead and change it so that we have smoothness instead of roughness by just adding a 1 minus. And now we need to adjust the value. We need to convert it from linear to exponential because our power value here needs it to be an exponential value, but what we have here is a linear value. And so what I'm going to do is use a material function that's called adjust smoothness. I'm just going to go ahead and grab this material function that I've already created called adjust smoothness. And I'm going to connect up my 1 minus the roughness value. And then I'm going to connect that to my power. And so now what I'm going to show you is as I change this roughness value, if I set roughness to a value of 0, our specular highlight's going to be teeny tiny because it's as smooth as it can be. And if I set roughness to 1, the surface is as rough as it can be. So now our specular highlight is just absolutely massive. And if I set it to 0.5, it's going to be halfway in between those. Well, let's go ahead and take a look at what's inside this adjust smoothness material function that I created. So I bring the value in, multiply it by 10, add 1, and then use this exponent 2, which is going to convert my data from linear to exponential. So you can see this is a really simple material function. I just bring in my value, multiply by 10, add 1, use an exponent 2, and then pass out the result. But this is converting my smoothness or roughness data that I'm storing in my texture, which is linear and goes from 0 to 1, to a value that I can then pass into my specular power. And this goes from a low power to something really high, like 1024 maximum, something like that. So I've converted my roughness to smoothness. I've passed it into my adjust smoothness material function, which I just showed you here. And then I can use that to raise my specular to the power where it needs to be. All right, so I've got my power value for my specular. Let's go ahead and save that. Oh, and we need to, there's a couple other things that I need to do here. I need to multiply my specular by my diffuse. And what this is going to do is, so right now, if I come around here to the back of the specular, I guess it's not really doing it in this example, but I need to make sure that my specular doesn't shine through the back. And so that's what I'm doing here by multiplying my specular by my diffuse value. Then we'll add in our diffuse lighting and our ambient lighting and get our final result there. And if we come back to our simple lighting, now our specular highlights are looking pretty nice. You can see that they're kind of speckly here, and that's because they're using that roughness input that's coming from my mask down here. Now, there is one problem with the specular, and that is it's really bright. Let's just go ahead and set our roughness to something where it's a little bit more clear. I'm going to disconnect roughness from here, and now you can see we've got a specular highlight that is pretty bright. Like most objects aren't this reflective. And so we need to add in a way to control reflectance. So let me just describe this to you. If I'm looking at an object straight on to the surface, most surfaces are about 4% reflective. And right now, the way that my specular highlights are working, they're actually 100% reflective. And that's not what I want at all. Let's just take a look, and let's just isolate this so we're just looking at the specular. So now you can see that my specular highlights are really bright, and no matter where I look at it, I'm just getting these really bright specular highlights. And what I want to do is adjust it so that when I'm looking straight at the object, my specular is kind of dim. But then as I rotate around so that I'm looking at the glancing angle of the model, that's where I want my specular to be bright. If you take a look at a flat tabletop, if you're just looking at it straight down, it's not very reflective. But if you lean down and make your view angle kind of perpendicular, or kind of parallel rather, to the surface of the table, you'll see that the table becomes really reflective. And that's the phenomenon that we're going to try to imitate right here. So we'll switch back to our material function, and the way that we're going to make our specular highlights dim when I'm looking straight at it, and then brighter at a glancing angle, is by using a Fresnel. So I will type in Fresnel, and there's my Fresnel node. And so what I'm going to do here is connect up our normal to the normal input. And then my exponent can stay 5. I think in Unity I set this to 3, but I think 5 is actually the more realistic value. And so let's just pass this out so you can see what this looks like. So there is the result of my Fresnel. So I'm making it bright around the edges or glancing angles, and then dim here in the middle. So we're reflecting at a value of 4% in the middle, and then 100% on the edges. And so what I can do is just take this Fresnel and multiply it by my specular, and then use that value as the specular instead of the original value that I was calculating before. So if we take a look at just the specular highlight, you can see that when I'm looking at it here straight on, it's kind of dim. We're only reflecting 4% of the light because I have this base refraction in set to 0.04. But then as I roll around to the edge, there you can see the specular highlight gets nice and bright because I'm looking at it at a glancing angle. And that's the effect that I wanted. Okay, let's go ahead and save this. And we'll switch back to our shader here. And now you can see again, our specular is dim here, but then bright as I look at it at a glancing angle. Okay, very cool. And now we can set up our shader to return the whole thing, diffuse, specular, and ambient. And we can connect up our roughness again to our roughness input. And then let's just go ahead and clean things up here. We don't need our ambient lighting here anymore because it's already in our material function. We don't need our blend and Phong. We don't need our Lambert diffuse. So we can just get rid of everything we don't need here. And we're just left with our base color, our normal map, and our masks. And our simple lighting. So what we can see here is instead of our lighting being calculated in our root node like it normally is, we're calculating it right here in this material function, and we have full control over our specular term, our diffuse term, and our ambient term. Right now, we're using very simple models. We're using blend for our specular, which is a very simple specular model. We're using Lambert diffuse, which is also very simple. And we're using this ambient model where we're just blending between a couple of flat colors, which is also simple. So what we've created is a very simple lighting model that's really cheap. In fact, it's probably several times cheaper than the lighting that normally Unreal calculates. And this can allow us to get significantly better performance in our project than we'd get in Unreal. Now, I will say this is definitely not as realistic as the lighting that Unreal calculates. But if you need an alternative to Unreal's lighting that is really fast to calculate and really simple, this is it. Okay, in the next couple of weeks, we're going to go over some additional things. Like, you might have noticed that there's no metallic input in our simple lighting. So next week, I'm going to show you how to create reflections and make surfaces that look like they're made out of metal. And then in coming weeks, I'm going to show you more advanced methods of computing specular, diffuse, and ambient, and we'll create a more advanced version of our lighting material function here. So stay tuned for all of that, and I hope you enjoyed today's video. Be sure to come back next week, and have a great week, everybody.